In this example, we will look at how a good choice of a ground or reference node can sometimes help to avoid having a supernode when solving a circuit using node voltage method. This is the given circuit. We can see that it has one independent voltage source and the circuit has one dependent source. Looking at this symbol, we have a minus plus inside the diamond symbol. So this means this component is a voltage source. And we can see that the magnitude is in terms of a circuit current. So this means this is a current controlled voltage source. When applying node voltage method, voltage sources, whether independent or dependent, can cause supernode to occur. So let's see what happens when we apply node voltage method to this circuit. So we need to first identify essential nodes. Essential nodes are where three or more circuit elements meet. So this circuit has 1, 2, 3, and 4 essential nodes. We need to select one of these essential nodes as a reference node. And in this circuit, it is a good choice to make this node the reference node. Let's see why. So we have two voltage sources in this circuit. So we need to check whether a supernode is formed or not. This independent voltage source is connected between ground and this node. So this means the voltage at this node has to be equal to 60 volts. So this means the voltage here is 60 volts. Because we know the voltage here and this side is grounded, this voltage source does not cause a supernode. Let's examine the current control voltage source. So this voltage source is connected between two essential nodes. So we need to see whether we need to form supernode or not. However, in this circuit, we can see that it is possible to determine the voltages at both sides of the supernode. And this is done as follows. So going from ground, we can see that this voltage source and this voltage source, the polarities add up. So that means the voltage at this node is 60 plus 6I5. For this current source, for this voltage source, since we know the voltages at both sides of the dependent current source, we do not need to find a supernode. So we do not need to write the supernode constraint equation. So what that means is we are only left with one node, one essential node where the voltage is not known. So let's label this as V1 and let's assume all branch currents are flowing away from this essential node. And now we can apply Kirchhoff current law to this node. So starting with this branch current through the 2 ohm resistor, this is given by V1 minus 60 over 2. The branch current through the 24 ohm resistor is V1 minus 0 over 24. And this branch current through the 3 ohm resistor is voltage at this side minus voltage at this side divided by resistance. So this gives us V1 minus 60 plus I5 over 3. So these are all three currents leaving a node and their sum is equal to 0 since there is no current marked that is entering the node. Because we have a dependent source in this circuit, we need to write a dependent source constraint equation, and that means expressing the controlling variable I phi in this case in terms of the node voltages. I phi is the current through the 3 ohm resistor in this direction. So we can apply Ohm's law to the 3 ohm resistor, and we can write I phi is voltage on this side. So that's 60 plus 6 I phi minus V1 divided by 3. This completes the process of writing the node voltage equations for this circuit. We can see that we have 2 unknowns, V1 and I phi, and 2 equations, and we can solve these equations to get the solution. Using the solve command in Mathematica, we can obtain the solution as follows. So V1 is 48 volts and I phi is minus 4 amps. Hence the obtained solution is I phi is minus 4 amps and V1 is 48 volts. Now we can solve for the circuit variables. In this case, we have to find the power dissipated by the 24 ohm resistor. We know that the power dissipated in a resistor is given by V squared over R. This is a convenient formula. And we can see that the voltage drop across the resistor is actually node voltage V1. So this means this is V1 squared over R, and substituting the values, we can show that this comes out 96 watts. So by definition, this answer is positive because a resistor always dissipates power. We can verify our solution using PSPICE. This is the same circuit simulated in PSPICE, and we obtain that the node voltage V1 is 48 volts as we calculated. We can also use LTSPICE to verify the solution, including the power dissipated. This is the same circuit simulated in LTSPICE. And if I bring the cursor on top of the 24 ohm resistor, we can see that the power dissipated is 96 watts, shown in the bottom left corner of the screen, and the node voltage V1 is 48 volts. So this confirms the solution.